All right, so hopefully you tried that out. Let's see what's happening here. So we have a magnetic field going from the north to the south. So this nice external magnetic field here. So there's my magnetic field. I have an electron going into the page, so that's towards my face. The field is going this direction, right? Going over to the right. So you can see that my palm is facing upwards. So the force acting on this electron here is upwards. That's my force, right? So what direction will it be deflected? It will be deflected upwards. Sometimes we'd say that's up towards the top of the page. If it's this going into the page, it's going to go up towards the top of the page or down towards the bottom of the page. So it's going upwards here. Now, what direction would an alpha particle? Now, an alpha particle is a particle that's charged 2e plus, or sometimes you just put plus 2e. So it's a positive charge. So what I'm going to do is I'm just going to erase this here. The field's going to stay the same. I just had to erase some other parts here. So I still have the electric field, or the magnetic field, sorry. Go in this direction. That's my magnetic field. This is now a positively charged particle traveling into the page. So I want you to, if you haven't done it already, pause the video and try to determine what direction that's going. All right. So hopefully you tried that out. Now what we're going to do is we're going to use our right hand to do this one. So my finger's going to go towards my face again, right? So I'm using my right hand. My fingers are going to go this direction. So my thumb, is going towards my face. That's the direction of the particle. My fingers are going from left to right. And then you notice that my palm is facing down. Because my palm is facing down, that's the direction of the force. My force in this case, for a positively charged particle, is going downwards. Now, the motion is very important here. It's like, what kind of motion is this particle actually taking? Like, it was getting forced downwards initially, but because it's getting forced downwards initially, it changes direction because force accelerates in that direction. So let's just talk about A, B, C, and D, and we'll come back down to D. D is a pretty important one. Same thing with B, but B and D, they're kind of connected together, just based on how you're looking at the picture. C is kind of connected to B and D, but you notice it has a little bit of horizontal motion. But the key is in A. In A, if the particle is moving in the same direction as the magnetic field, you notice that when we do the hand rule, using the left hand or the right hand, if I'm using the hand rule, everything is at 90 degrees to each other. So I got the field going upwards, the particle traveling sideways, my palm coming out of the page here. Everything is at 90 degrees, right? So if I were to try to use the hand rule, I'm not going to be able to turn my fingers. I can't move my thumb. I can't move my fingers. Everything's kind of stuck this way for this hand rule. Now, if I want to try to do this diagram here, I'm going to put my thumb in the direction that's moving. So my thumb is moving the direction to the left there. And I want to put my fingers in the direction of the field. Okay, so no matter what I do here, I can't seem to figure out how to get both of those pointed in the same direction because this has to stay at 90 degrees for this to work. I'm like, okay, so this is not going to work. Now, there's no way for this to work because what's happening here is there's no vertical component here. So the vertical component of the speed is 0. This doesn't actually exist. This is all horizontal, so that's parallel. So there is no force here because it is parallel. It has to be perpendicular to be a force. There has to be some kind of perpendicular speed. And if there's no perpendicular speed, there's no force. So in B and D, you can see that there is a perpendicular speed. This is going upwards here. So if I were to do that, so it's going upwards. I got my field going towards the right to the or left to the right. You can see my palm is being forced out of the page. So there's going to be an initial force right here out of the page. But then something weird happens. It kind of wraps around and it goes in this kind of weird circle here. So it's going out of the page and then it goes back into the page up here and then back down to the other side in this kind of weird circular motion. And we can see that a little bit easier if you go down to B or D here. So let's imagine that we have an electron. Let's do an electron traveling this way to start off with, okay? So my electron is traveling this way. So I'm going to put my thumb in that direction. I'm going to put my fingers into the page. So my fingers are going to go into the page. You notice that my palm is facing upwards when I do that. So when I put my thumb in that direction, so my thumb in that direction, the fingers into the page, because my fingers are the magnetic field, you can see the magnetic field is going into the page. My palm is facing upwards. And because my palm is facing upwards, there's a force acting on this electron. Let's just imagine it got this far before the force was interacting on it. Force is acting upwards. There. Now, because that force is acting perpendicular to this motion sideways, it's going to change the vertical velocity. And when it changes the vertical velocity, it gets deflected upwards. So let's imagine it's here now. Okay. Now, when it's here, now it's moving this direction. So remember tangent speeds from physics 20? If you're spinning something above your head and you let go of it, it's going to travel at a tangent to where it was on the circle. So now it's moving this direction at this point. So that's the speed of this object, or the velocity, I guess. So you're going to put your thumb in that direction now, right? And then you're going to move. This is going to be a bit weird, okay? So it's going to go into the page. This is going to go up, and then you're going to tilt it this way. Then as you tilt it upwards, you can see that the force also tilts. So the force now is going off in that kind of direction there. So now if the force is going off that direction, it's a little bit easier when you can do it. Just put your hand into the page, your thumb in the direction of the particle, and then you notice that which way your particle is moving. So there's a force here. Force going that way. So now, because that force is acting perpendicular to its motion, it's going to change its direction, that direction as well. Sorry, that direction. So now at this point, it's traveling upwards. Okay, so you do the same hand rule. Okay, so traveling upwards, feel into the page. You notice that my force is going this direction. So at this point right here, there's a force acting inwards. Okay, then now it's here. It's changed its direction, and now it's pointing that way. At the top here, now it's going this way because it changed its direction again. So the force is inwards again. It changes its direction. So now it's traveling that way, and so now it's going to keep on doing that around and around. Because the force is always going to be perpendicular. Now this is very key for circular motion. When we dealt with gravitational objects orbiting, like the sun and stuff, the gravity was always acting perpendicular to the tangent motion of the object that's orbiting, right? So if the force is tangent to the direction of the object, or sorry, perpendicular to the direction the object was moving, it's not going to change its speed. It's going to change its direction, but its speed stays constant. So it creates what we call uniform circular motion. And because the same idea, this force here is perpendicular to the tangent speed at all points around this circle, it's not going to change the speed. So the speed of this object is constant. The speed is. So you notice I didn't put that in there. So let's get rid of this and just write speed. The speed is constant. Oops. Okay. The velocity is always changing because the direction is always changing. But the force is only used to change the direction. It's not used to change the speed of the object. Okay. So that's why it creates this little circle. It's creating a little circular motion because the force is always changing direction as the object moves around. And you can see that's what's happening here. It's creating this little circle, but it's also creating a little spiral because the parallel velocity, same thing up here, there's no force parallel. The parallel magnetic force is 0 on the parallel part of the velocity. So the force is only acting on the or perpendicular velocities. So the force is only caused by this piece here. This piece, because there's no force in that direction, in this direction, going across the page, I guess that way, right? This force is 0, but there's a force on this one. This one's not 0. So my perpendicular part is not 0, so it's going to create that little circular motion very similar to what we have in D here and B. But because my side motion doesn't change, this object will just keep on drifting to the side. It'll keep on drifting left there. All right? So that's what it looks like. It's got this circular motion. Because of that circular motion, we're all going to use some circular velocity or circular speed formulas or circular acceleration, centripetal acceleration formulas to do this. All right. So how do we figure out the actual force of this? Just 1 second. All right, so how do we find the actual force acting on this charged particle as it moves through this magnetic field? So to figure that out, it's actually quite easy to do. To find the direction, we use our third hand rule. Okay, that's not too bad. But to actually find this force now, because the force is a vector, we needed the direction, right? So we find the direction using the third hand rule. That's pretty easy, right? I use that flat hand rule to do that one. Now to actually find the force here, it depends on a few different things. And you can kind of think about logically how this actually works. Well, if I want to determine the force, I need to know the strength of the two fields. So I want to know how the fields interact with each other or how the fields are generated. So one of the fields is generated by a particle that is moving. So that's where this Q and the V come from. This is the moving particle. Moving particle. Okay. Either positive or negative. So Q times V, that's the charge of the moving particle, the moving charge. And you kind of think about this as that if my charge increases, my magnetic field should also increase, okay? And then I also have the perpendicular velocity. The key is at the perpendicular velocity. So there's the little perpendicular piece right here. So the velocity has to be perpendicular to my magnetic field for this to work. Not parallel velocity, but it's always the perpendicular velocity. Now, there might be an extra piece here, like a cos theta, to kind of correct that, but you're always looking for the perpendicular velocity, so you're going to have to maybe use some trig to find out that piece that's perpendicular to the field itself. Okay. Now, also, if you think logically, if I'm moving faster, because the charge is moving faster, the magnetic field is also increased. The strength of that magnetic field is increased. So a charge that moves produces a magnetic field. And if you put that magnetic field in another magnetic field, this external one, it produces a force, right? So the formula is pretty easy. It's just Q is equal to, Fm, the force, the magnetic force, is equal to QVB. And there's lots of absolute values here because this formula does not help you find direction. It's the hand rule that helps you find direction. This formula will only help you find magnitude. So I have this applet here, this GeoBra applet. Couldn't quite find that one, but there's another one that's very similar to this one. I can now actually find it to see if that actually works and find out some things about how a charged particle moves within a magnetic field. So let's imagine that we have a negatively charged particle. Okay? We have a field here. I can change the direction of the field both ways here. So let's imagine I have this field. Actually, let's do one that's coming out of the page. Okay? So I got a negatively charged particle moving into the field. So it's going this way. So you can see I start it. It's going to go that way. My field is coming out of the page. My palm is going upwards here. So you can see that the force pushes it upwards. And then as it changes direction, the force keeps on changing direction and creates a circular motion pattern here. You can see there's a constant radius here. So I can actually get the radius if I wanted to. Okay. So if I wanted to, I can actually figure this out. Let's put that there. Let's put that trace in there. So this is a -2 charged particle, so it's not quite the same as an electron, but we can get down to, well, I can get more negative. So if I increase the charge, I'm not changing anything else, the mass stays the same, the velocity of this object stays the same, everything else stays the same. If I start this, because my charge is increased, I should have an increase in force. That's what happens. Yeah, my force increased, so I give a sharper angle to that. Okay. So let's put that back down to -2. If I increase my velocity, I should also increase my force, but the problem is that when I increase my velocity, I'm increasing the tangent speed as well. So the force increases, but I was moving faster, so the arc didn't change. It actually got a little bit wider, but the force got bigger. Okay. put that back down to kind of where it was before. That's close, okay? Then if I change the strength of this magnetic field, that should also increase the strength or the force. You can see that it also increased the force as well. If I go the other direction, you can see it's going the other direction as well. If I change it to a positively charged particle, you can see that it goes the other direction based on the other hand rule. So this is going this way this time. So out of the page, or actually towards my face, this way. That's kind of weird. Okay, and then it's getting forced upwards. All right. The mass part is later on. We'll talk about how the mass affects certain things, but you can think about that. If I increase the mass, let's reset most things here and just shoot off one of these. So that's what it looks like here. If I increase the mass, you can see what happens. Now, the reason that happens is because there's more mass. It takes more force to change its velocity, so the arc is a little bit bigger. All right. Let's go back to my thing. So the formula is pretty easy. It's just QVB. That's all it is. We come back to it later on. You'll see later on when we talk about a wire. What is this B? So a B is a Tesla. If I want to know the units of a Tesla, so I'm just going to rearrange this equation for B. So that's going to be FM divided by Q and V. Okay. Now, an FM is a force, so that's a Newton. A Q is a charge, so that's a Coulomb. And V is velocity, so that's meters per second. So this turns into a Newton second over Coulomb meter. And I probably could break this down even more if I wanted to. A Newton is a kilogram meter per second. I'm going to times that with a meter or a second. I'm going to divide it by a Coulomb and a meter. So the meters cancel out. One of the seconds cancels out. I'm left with a kilogram per Coulomb second. I think that's right. So seconds here goes to the bottom. Those are almost meters. Yep. So kilogram Coulomb seconds. Okay. So that's essentially what Tesla is. All right. This is a capital T, so that's a Tesla. Named after Nikola Tesla. Okay, so we're going to stop this video here. We're going to talk in the next video. We're going to do some examples. How do we use this formula to solve some questions, determine the magnitude of forces and stuff, and maybe even directions. I have this picture here. I probably determine the direction as well. And we're going to do a few of these examples in our next video. Okay, I'll see you then. Bye.